Hi everyone. Excuse me for sitting down. I've got some really bad back problems at the moment. Welcome to session 2 of the Asia Pacific Research Platform session. I'm going to be kicking off with a quick NCI update, and then we'll hand over to our next speaker, Keon Kim from KISTI. Okay, well, without further ado. I'm Andrew Howard, Associate Director of Cloud Services and Innovation at the National Computational Infrastructure in Australia. We're actually part of the Australian National University. In Australia, it's traditional that we pay our respects for the traditional owners of the lands on which we meet. And in Canberra, that's the Ngunnawal and Ngambri people. We are quite active in terms of our Indigenous engagement. And we have Indigenous artwork for all of our systems. So I'd like to give you an introduction, quickly explain what NCI is for those who have not seen this before, talk about our new director, but more importantly, our Near Cloud refresh that we've been waiting for several years. So we've had some change of staff at NCI. Our former director, Dr. Sean Smith, left the ANU and NCI in 2024. Professor Andrew Roll commenced on the 24th of March 2025. Andrew Roll, Professor Roll comes from Curtin University in Western Australia. He's had a long history of supercomputing use. He's been an NCI user for over 10 years. So it's really refreshing to have a director who knows exactly what our facilities are supposed to provide, and then holds us to a high bar in terms of his expectations of what we'll deliver. We're also joined by Dr. Hannah Rodriguez Colombo. Hannah is our Chief Operations Officer. So she's looking after a lot of the administration work, making sure that we've followed up on contracts. I'd also like to thank our outgoing Provost Chancellor, Professor Uta Rosner. Uta was appointed the CEO of the Australian Research Council. That's the organisation which hands out around $2.5 billion of research funding within Australia. So it was an absolute pleasure to work with Dr. Rosner, or Professor Rosner, over the 18-month interim period between that. So NCI is Australia's one of Australia's 2 high-performance computing facilities. We provide a comprehensive vertical range of services. Our sister centre, Pawsey, over in Perth, deals primarily with the square kilometre array and radio astronomy and mining. So NCI supports all of the rest of the disciplines of science. We do have some prohibitions in terms of what we can work on, which is anything nuclear energy related or anything in terms of weapons production. Unfortunately, our Department of Foreign Affairs has not allowed us to participate fully within the APRP, providing additional resources. We have provided some initial resources in there, but unfortunately, we're not able to provide a stable production workload environment for the APRP. We're really sorry about that, but unfortunately, my hands are tied with our Department of Foreign Affairs. We cover the complete spectrum of science, ranging from fundamentals, strategic, applied, and then industry engagement. So start up looking at the initial results, then progressing towards operational systems, which support a number of programs in terms of disaster management, national collections, data portals. We hold around 120 petabytes of data in our main computer centre. So our systems, NCI is quite different from from other HPC centres in that we have a close coupling of our HPC, our cloud, and our high-performance InfiniBand storage environments. So users can start off on the cloud, perform their initial development, then migrate that workload as a container into our HPC system. We also have a graphical front end for our HPC system called Australian Research Environments. which is built on the Open On-Demand software that's kindly provided by Ohio State University. That gives our users a single web-based interface into our facility, meaning they don't need to wait for their central OT department to go and install additional tools on their laptops or workstations. They can just get going straight away into their environment. Within that, we have a range of applications, including Jupyter Notebooks, Jupyter Hubs. That allows users to submit onto our GPU systems. So they're able to get the full use of all of NCI capabilities from a single pane of glass. But computation is only there to extract the value of data. While as engineers, it's really cool to build big computer systems, do the power, water, cooling, all of the other stuff that you don't think about when you do computer science. There'll be an electrician and a plumber down the path. It's great to have a bit of diversity in having to learn new areas and new disciplines in engineering. So what I'd like to really talk to you today about is our cloud systems. Our cloud is called Nirin. Nirin comes from the local Wiradjuri word, which is one of our First Nations groups, and it means the edge. Our Nirin cloud is an infrastructure as a service platform based on OpenStack. This allows us to deliver edge case services, which fit alongside and support our traditional HPC workloads. The things I'm talking about are our data portals, long-running applications, long-running web services that don't fit into the traditional queued model of submitting jobs into an HPC system. But you can certainly do that from Nirin. So the front end runs on Nirin as a web service and then leverages our HPC in the back end for high performance computing. Our cloud was originally built from our former supercomputer. We try to extend the life of public taxpayer money as far as we possibly can. This was probably a bit of an extreme extension, but it has served us well for the last 6 or 7 years. We originally started with a 22 rack footprint. Over time, the elements started to fail. We had around a third of the old supercomputer as spares, which we're now starting to burn through. So what we've started to observe is the failure rate of 10-year-old hardware is accelerating over time, which has prompted us to do a complete upgrade. Now, our old cloud, and we've integrated a whole lot of elements of the CPUs, whatever is still currently operational and working, we're able to build a heterogeneous compute environment to deliver specialized services to specialized communities. Things like Octane large memory nodes. So we have 4 3 terabyte memory nodes. We use those for things like Redis, in-memory databases for our genomic stores, or applications which require a large amount of memory. The most typical of those is a genome alignment, which is fully able to utilize massive memory capabilities. We also have some very old K80 GPUs, which even though nobody really wants those anymore. They want A100s or H100s. Instead of investing those into the cloud, we put those into our HPC facility, which provides the most value for the wider range of users. Early this year, we were given 1.25 million Australian dollars to perform a hardware upgrade. As I mentioned, this is a CPU-only upgrade. It replaces Sandy Bridge 32 nanometer microarchitecture, which was released in 2009, with the current 5th generation AMD 9005 series Turin CPUs. So we were actually very privileged to have pre-release hardware for Turin, and that convinced us to actually purchase around 2 racks of Turin, which provides the same compute capability as 12 racks of Sandy Bridge. As part of this, we also upgraded our 40 and 56 gig Ethernet. We're also using old Mellanox cards, which we switched from using InfiniBand mode to Ethernet mode, once again, just to extend the life of everything that we possibly could. It all fits in 2 racks. However, this is a significant increase in power density to the rack, So there was some electrical work needed to consolidate and put more power and cooling capability into those two racks. Each of the machines is 2 sockets with an AMD EPIC 9535 64-core processor. So we have 128 cores capable of running 256 threads in each of the nodes. We've also added another 6 petabytes of Ceph storage. We've been very slow in upgrading OpenStack. We typically take the approach that if it isn't broken, don't fix it. However, having all this new hardware has given us the incentive to upgrade multiple versions of OpenStack. And one of the things that the team have done is develop a hyper-converged infrastructure. Now, what this means is we run our undercloud or control plane across a number of systems. Each of those systems is supported by Ceph. So there's a shared file system running across the undercloud and volume and object storage services like S3. So we containerize all of the control plane. This allows us to run 3 distinct environments using the same nodes and allows us to migrate from our development through test and into production completely transparently to our users. So we typically run a 99.99% uptime on our cloud, but it gives our development teams a whole lot of flexibility in terms of testing without worrying about breaking our production services. So our HCBI implementation, which is what I'd really like to talk about, is a custom-built virtual infrastructure of containers, all running on shared hardware. As I mentioned, we've got development, test, and production OpenStack deployments, which each have their own set of containers. And inside the containers, we run virtual machines, which implement various parts of the control plane services. This also allows us, at some point, if we wish to de-aggregate the services into containers across the HCBI system. Each deployment's resources, network, compute, storage services are plumbed into the containers, and the containers map these resources into a standardized layout within the virtual machines, being presented into an abstract view of the deployment's resources. We also have abstracted the environment, ensuring the configuration for easy deployment, for the deployment to make sure they're essentially identical, allowing us to minimize maintenance and development overheads. Niren supports NCI services delivery, our public-facing services. We support about 60 petabytes of externally facing curated data collections that are AI ready. We have data analytics and dashboards, data inflow and processing with DTMs, service portals, virtual laboratories and research environments, typically based around open on-demand. Niren is also the delivery platform of our stakeholder services. So we do what we call eating our own dog food. We use our own systems to provide externally facing services for the academic community in Australia and globally, but also provide infrastructure as a service for our users to build everything from the ground up for a customized environment just to suit them. So our national computational infrastructure, we're currently going through a process called the NDRI, the National Digital Research Infrastructure Roadmap process. This is a $400 million federal government funding stream. NCI and Pawsey, our sister centre, are jointly submitting proposals for infrastructure refresh across both facilities. We have actually had the announcement, even though we asked for $115 million, we've only received $55 million. So this is going to mean we have to engineer and utilise our old HPC system, add another additional layer of new CPUs and new InfiniBand capability, and extend the lifetime of what we currently run. So NDRI provides opportunities for all of us. There are 4 elements in Australia that are the underlying foundational capabilities. NCI and Pawsey as the 2 HPC centres, the Australian Research Data Commons, which also have their own cloud and do data services, and ARNet, our Australian Academic and Research Network, which connects support to us all together. I just really like to put this into a context of where we are network-wise. Australia is the furthest network element anywhere in the world. Now, this requires specialised tuning, which we've submitted upstream, and has now become the standard tune for data transfers from Europe and America to Australia, maintaining full operational performance. We're also using BBR, which was why I was really keen to see that as something that our colleagues at KISTI have been experimenting with. We've also got very good results out of that. So that ends my brief presentation. We're probably a little short of time for questions, but grab me during the break. I'm pretty easy to spot. Happy to answer any questions going down to the deepest technical level on networks or our systems. But thank you for your time. We'll now hand over to our next presenter, Keon Kim, for a proposal for Korea-China joint research.
Yes, it is.
Go for it, Keon. Can you hear us?
Can you hear my voice?
We can hear you fine, thank you. And seeing your presentation well.
Can you show my I started the presentation?
Yes, we can see your presentation and hear you fine, so please proceed.
Okay. Hello everyone. My name is Keon Kim. I work at KISTI from Korea. I presentation on the recently proposed joint research project between Korea and China. Yeah. CRONET provides a virtualized, intelligent, programmable network infrastructure through the construction of an STM-based wide area research network. This infrastructure is called CRONET S. And from now on, I will first explain the CRONET S infrastructure and then explain the Korea-China joint research project. CRONET S means CRONET softwareization, and CRONET is the national research and educational network infrastructure in Korea. CRONET has international network connections with Gloria to the United States, China, and Europe based on up to 200 gigabps network bandwidth. CRONET S started in 2015 to softwareize CRONET and Gloria using SDN environment. First, CRONET S users are mostly from advanced R&E and science community, and their requirement for new networks are three things: auto-provisioning of resources over SDN-WAN, end-to-end resource orchestration with intelligent network services, and a very high network performance for up to 100 gigabps data transfer. So the virtual networking services are demanded for the CRONET S users. The principal researcher who conducted the project at the time was Dong-Kyun Kim of KISTI. CRONET S infrastructure is as follows. The control plane utilizes the open source owner's controller and is distributed across Daejeon and Seoul, composed of one build machine and three deploy machines. The control plane can be replaced by another controller if a problem occurs, ensuring uninterrupted service operation. The data plane utilizes switches capable of supporting the open flow protocol. Brocade, Arista, and Ethical switch devices are deployed and operated at regional network centers. OpenV switch, the virtual switch can be used to configure the switches in a virtualized environment. The current diagram shows the current configuration of the current S infrastructure. Data planes have been deployed domestically at regional network center in Daejeon, Seoul, Busan, Changwon, and Gwangju, and internationally in Chicago and Seattle and Hong Kong. The equipment deployed domestically is connected to organizations requiring SDN networks in each region of providing services. Furthermore, a Korea-China joint research project will be conducted using the switches deployed at the Hong Kong International Network Center. Various applications have been deployed on the application plane that operates on the owner's controller of Planet S. Among them, VDN is provided as a killer application. VDN is a virtual dedicated network, a service provided by the current S infrastructure, and provides a virtual dedicated network that guarantees a specific bandwidth to researchers. As a feature of VDN, bandwidth, path, and so on can be customized according to the research field and requirements. And virtual network can be created and deleted immediately as needed. And it supports high bandwidth for large capacity data transmission and real-time collaboration. It contributes to improving research performance by providing an, uh, an efficient collaboration environment between researchers. As shown in the figure, Gradient Slice 1 guarantee a bandwidth of 1 giga bps when configuring data transmission performance between four hosts between Daejeon and Seoul at 1 gigabps. The second application is Gradient Federation technology. Gradient Federation is a technology that enables network connectivity between two different SDN domains. Inter-SDN connectivity provides guaranteed network performance across various SDN control domains via SDN WAN, which is intended for inter-SDN connectivity and resource federation. The VDN Federation can be used to connect SDN networks between Korea and China. This will be explained in more detail later. Now, I would like to explain in detail the Korea-China Joint Research Project. The project is called Intelligent Transfer of Big Science Data over China-Korea Software-Defined Interconnect Connections. The research period will be 3 years from January 1st 2026 to December 31, 2028. Uh, the research budget is 180 million won. The proposal submission process is currently complete, and the results are expected to be announced in October. Uh, the main research and development activities are as follows. First, establishment of Korea-China International Software-Defined Data Transfer Environment and interoperability. Second, joint research and development of on-demand virtual network slicing automation and resource reservation management technology optimized for big data. Third, joint research and development of high-performance big data transmission technology through virtual network slice allocation using QUIC technology, a high-performance transmission protocol for Korea-China science big data. The QIC protocol is a transport layer protocol developed by Google. It aims to improve the shortcomings of the existing TCP/IP protocol and enable faster, more secure, and uh, more efficient internet communication. It contributes to faster web service speeds and serves as the underlying protocol for HTTP/3. QIC operates on UDP for faster connection establishment than TCP and supports zero round trip time during connection establishment, reducing uh, initial connection latency. As above, we plan to proceed with the main contents of the three areas through assignment. For this project, we conduct a project with CSTNet in 2018. Utilizing CSTNet's SDN network and KISS SDN network to conduct a federation. The following figure illustrates the two networks being conducted, the host-to-host data transfer test conduct. This figure shows the VDN federation in progress and shows the network environment for each port where VDN federation is performed for two networks as shown in the lower right. The SDN network domains established in Hong Kong and Korea were conducted via federation, allowing network hosts in Korea to be identified from the Korean side. Once this project is complete, we will establish an environment that guarantees bandwidth for data transfer through VDNs between these connected SDN domains. Afterwards, we plan to conduct experiments on large-scale data transfers between connected hosts using the QIC protocol. Thank you for listening to my presentation.
Thank you very much. Unfortunately, we're running a little late, so we don't have time for direct questions. If I think Junhun is able to provide any introductions needed.
Okay.
Our next speaker is Kanamaya Hidetomo from Riken JP, talking about big data file system.
Thank you. And they open the hello, you are so I'm Tayana, I'm from India. So I'm India in RCCS, in RCCS. So today I will introduce the efficient calculation system in RCCS. This is the big data and the political data RCCS. So this system works for efficient data is created to the use of data in Japan. Okay. Next slide. So first, so it is what is the HPCI? So in Japan, so HPCI is a natural project to use like domestically so produced so supercomputer in Japan. So HPCI manages the infrastructure for use and access to the supercomputer in Japan. So HPCI will provide free program for infrastructure and service. So we have so many sites, efficient and many sites and infrastructure. So efficient provides network storage systems to other so share so data between the data and researcher. So this is the efficient storage system. So it is a efficient storage system overview. So efficient storage is one part of the efficient infrastructure. Currently, the efficient storage is operated by the University of Tokyo and RCCA. So we have two hubs. So efficient storage service so backup all data so between the locations. So University of Tokyo and RCCA. So the storage so capacity will be the 95 petabyte. Yeah. Yes. And so 2025 from that 2025 is October. So currently we are updating and building new systems, so third generation systems. The efficient storage system use the GPAN file systems. So it is the open source and the network file system. And this GPAN file system is developed by the Professor Takebe in my university. Next is also efficient storage system history. So efficient storage project was started in 2012, and first phase capacity is only 10 petabytes. The second phase is started in 2018, and 2018, and the capacity is upgraded for 40 petabytes.
Yeah.
So our network is upgraded to 100 years, and very fast network storage at that time. So currently we build so third phase systems, so third generation systems, and the capacity so includes the 95 petabytes or more. It can very wide bandwidth to over 800 gigabits. So this is the overview the third generation systems, and so main storage in the here in the so NVM so NVM2. This is and so we use the hard disk storage. So the NVM and NVM2 the virtual machine to be installed on the storage controller, and so we have so installed GPAN file server in the virtual machine. We don't use physical server so for the GPAN file servers. So each unit so we have so each input so has the I/O performance is so 32 gigabytes per second. Very powerful storage, and so install 10 units. So I/O total I/O performance of the so 320 gigabytes per second, or about the 2.5 terabps. You have very wide bandwidth to this network storage systems. So as a result, so the internal network went to the upper switch. This is the upper switch, and 1.6 terabps and connected. And so actually, so just connected from the RCC to the target is here. It's so 800 gigabits bandwidth, very strong bandwidth. However, this system is so built to use only handbricks, right? So I opted that the SFP protocol, right? And if you so performing the IO on small files, so user need to the transfer the data to use the local archiving. So at this reason, so we provided an API on the command. So for the automatically so archiving when the transfer to the data or data. So this is the third generation institutional solution performance. So performance upgraded from the second phase, second phase to the third phase to upgrade. But so however, capacity is only from 2 times, yes, 2 times. So this reason is so we have not provided and so if we do it again, so no feedback. So this photo is a third generation system photos, and we use the local cooling environment here. So because we so assign turbines, so that's a cooling, so cooling air conditioner, without air conditioner. So we have to find a way to cool the cooling systems. So photovoltaic right to interact. So this is the photovoltaic system CPU, and so supply the interacts. And so cold air is and cold. So and use the cold real air cooling systems. So this is the cooling unit. So this is the fan. So and the supply the water to water and so this is the cold cold storage system. So that so this is fan. So this is this makes very noisy just the GPU machines. So and the storage is over so 1,000 kilobytes. It's US from. So this photo shows so reinforcement verbs. So being to carry out from the supported heavy slabs. This one. And it was also necessary for the extended pipes to connect to the water cooling system, so CPU. Also, so it was a simple construction work. It took the long time and long effort, busy effort. So very heavy jobs. So this is the management environment plans for build the phase systems. So we need to scalability systems for the system monitoring and management systems. So we entered so set up the monitoring so Kubernetes with the Kubernetes layer and so virtual machine layer, then using the blocks mobs. And so set up monitoring system. So we have analyzed and famous monitoring systems we use. So this is the monitoring views. So this is very sorry, so we have the so and so this is for items, so you are not an images. Not very big stats and not an environment or very important things. So we are developed the social folder. This is on the folder, and so we developed the smart connected folder. And the future work is partly the upgrade monitoring using to the EVPF and the GNI protocol. And secondly, is the political introduction of the PCM and AI, so the integration. So we must that the whole part is so alliance. So this is the last slide. So future, okay, last slide. So this is feedback. So we publish from the workflows for the expanded adaptation. So that concept, this concept overview was announced at Shinajira 2024 conference. And the detail will present. Detail is will be present at the international data week 2025 so in October. So HPC workflows using the local file skills so the computer is not computing. So many currently so currently the HPC storage sorry. So now so if currently the HPC storage is so for example the raster and the BGFS and so it not have the so expanded variable only for time and the file size, but so we need to the more metadata. So this is a little program so for the open science and data sharing. So and also sometimes user cannot search all data, so all data in the themselves. So we have problem. So currently many users so do not remove the full data in a digital storage system. This is a very big problem. So this is a concept for manage the metadata, so full data, and digital environment is that so facing the changing the changing the so service or systems. So this is the overview for management from the expanded data to use the way workflow tools. But expanded data is automatically assigned in the supercomputer. So calculated using the way workflow tools to pass and so next is the right was archiving right and the safety check of those systems. So the expanded data is so with writing in the Excel format, expanded data, so is writing the Excel format database in that here, so we say here. And so the check of the systems. So the data category can be searched using the GPAN file system API and command search. This is very simple mechanism, but very strong mechanism. Future goal includes so more production of the platform, this platform. So this is future work. So provided from the web servers and the other source to use the expanded. So that is a commercial. So SGA and API will be held in the so January 2026 in Japan, Osaka. But so it is over to the APAN60 very much. Yeah, thank you very much to the finish. Please.
So we don't have time for questions. We're running a little bit late. If I could hand over to our next presenter, and please, my apologies if I don't get your name right. Kim Kim from Yonsei University in Korea on research platform for medical. exome is screened quite well. Thank you.
Yeah. Okay, thank you, Dr. Howard. Thank you all for joining. So I would like to present about how research platforms are used for genome editing, which is a key biomedical technology. So genome editing is a method to change, add, or delete certain DNA sequences in a genome, such as those causing diseases from DNA mutations, like cancers, or hereditary genetic disorders, such as multiple sclerosis. So the genome defines how life works, and therefore genome editors edit life functions. There have been various generations of genomic editors, and I believe that CRISPR-Cas9 is a well-known name. So CRISPR-Cas9 is composed of a protein enzyme named Cas9 and a guide RNA that is designed to target a certain genomic DNA sequence. An alternative form of genome editor named CRISPR-Cas13a can target RNA sequences. Because RNA is an intermediary substance between DNA and proteins, because proteins become traits that we can observe in life, Cas13a is a less invasive form of genome editing. So these genome editors such as CRISPR-Cas9 and Cas13a are able to edit the transcriptome as well as the genome. One major application of genome editing is in biotechnology and agriculture. Genomic editors can accurately activate genes that lead to various improvements or deactivate unfavorable genes. This is done with high precision, as genome editors are also applied to human therapy. In contrast, traditional GMO needs to introduce completely new genes into the plant or other organism, which leads to various complications. Genome editors only edit a certain region of the modified organism, which leads to additional advantages. Moreover, genome editors are actively utilized in clinical applications after just 13 years of discovery since 2012. Casgevy has been recently approved to treat sickle cell disease and beta thalassemia, and various other hereditary disorders have also shown success stories in the treatment of disorders in the eye and the ear. Cancer immunotherapy is also a key application. In stem cell transplantation, patients can use an edited version of T cells that originated from their own bodies, which can find and fight cancer cells much better. And other clinical trials are also ongoing with high potential. Genome editing, however, still has some various challenges to be solved. One case is off-target editing, where the DNA gets edited in an unintended location. This is especially important for clinical usage, where errors are not permitted. Moreover, editing activity is inconsistent in different target genomic sequences, leading to reduced efficacy for some disease genes. Furthermore, there is a dependence in a sequence named PAM sequences, as this is the detection point of the Cas9 enzyme. Finally, delivery to the target location, such as organs or tissues, is a challenge. All of these issues can be solved with bioinformatics and AI, and that is what we do in the Yonsei Genome Editing Laboratory. Our group specializes in bridging the gap between wet lab and dry lab tasks in genome editing. We combine large-scale, high-throughput screening of genome editors with prediction based on machine learning, providing very impactful results. We are also interested in recent artificial intelligence technologies such as structural models and language models. One key successful field that we have paved is off-target activity detection where we predict unintended genome editing effects through deep learning models. Feature importance analysis, such as Shapley trees, also provides biochemical insight into which sequence location or feature is most important for genome editing. Recent developments have also led to a completely new enzyme protein, for example, OpenCRISPR-1. Of these applications, our focus is to utilize wet lab results in a deep learning model to predict the activity of genome editors for a specified target sequence and guide RNA combination. As our results lead to a massive reduction in time and cost for other researchers using genome editors, it is important that we provide this result to researchers worldwide. Our solution is a web server. We have provided web interfaces for researchers to utilize as part of our many successful publications and results for many years. And this is where the National Research Platform, also called the NRP, comes in. If any of you were in this session in March, you may recall that the NRP is both a data freeway and a cloud supercomputer. The Nautilus cluster of the NRP provides a key community-based cloud platform that fills between the gap of traditional HPC and commercial clouds, where both of the intended roles are possible. KIST has thankfully supported us with their Advanced Research Support Program and provided a 10G Science DMZ network to utilize and contribute to the NRP. One key component of our new web server is to combine job scheduling and a web frontend. Kubernetes is an excellent platform for this purpose, and Nextflow allows us to receive input from a web interface and schedule Kubernetes job resources. Kubernetes is a comfortable middle ground for ML ops workloads between Apptainer, known as Singularity containers, and Docker container platforms. The following is a proposed schematic for a web server and job scheduler. And here you can notice that this is a very similar technology stack to the CrayoNet AI initiative and the Korea Research Platform. We anticipate that this approach provides a real-life usage case applicable to the APRP as well. We hope that through this project, we can propose a unified web interface for our successful web servers, where we originally managed each web server separately. Moreover, certain journals highly encourage the deployment of reproducible and accessible resources for already existing research results. Overall, we consider that our deployment approach would greatly improve the experience of researchers using genome editing technologies, as well as improving the stability of our web servers. Finally, we expect production experience for MLOps workloads for the APRP's architecture based on the NRP and CrayoNet AI. Thank you very much, and I also thank KIST and other funders for their support.
Thank you for an absolutely amazing presentation. The work you're doing is absolutely groundbreaking. Thank you for really pursuing this on behalf of the whole of humanity.
Yes, thank you, Dr. Howard.
So our next presenter is Xiangli Zhang from NSCC in China. We'll be talking about distributed HPC in China.
Yes, no.
Computer detail.
Can you access the Zoom? No? Access Zoom?
Yes.
Oh, here it is screen. Is it possible we have problems with Mac?
Oh, so no people.
Oh, okay. Just go there.
Forward and yeah, go.
Yes, the bring your
Okay.
and go the beside cable. The direct cable. Yeah. It's yeah, and then sit the chair.
Okay, I guess. Okay, there we go. Yeah, thanks, Andrew, for hosting, and I apologize for changing the topic. I think it was distributed HPC in China, but the topic was too big and broad, so just make it more specialized, and it is a very camera and still ongoing project. It's APAN60 is dual bridge group app, instead of group app for practices and researches. The name is ESCD-AI. First, I will explain why it is called ESCD-AI or PCD. Basically, ESCD is from the university name, Stanford University DI. And the CC comes very initially the project for cost teaching. It just for the combination course, so it from the GCC compiler. So together it is ESCD. But you can see, we are more and more ambitious. Because the bottom three, you can see we make the young training, including agility and young, and also the final one, yeah, the creative cloud. So it means we want to have the platform on the supercomputer and for very general uses, both the practical training and also the open science researches. And the top picture is our team, yeah, many composed of students, or level students. Okay, I will quickly introduce more. First, yeah, the big picture, the background, application keeps scaling. And in the past decades, we've seen the EPC and the application grows. And the first year, the traditional EPC applications just continue growing. And in the past couple years, you will see the emergence of AI and particularly the large language model. See the growth is even more significant, right? And can be our hundreds of times scaling. And we've already seen that, yeah, the large language model training and inference can be very efficient on the HPC clusters. But yeah, HPC cluster is not only for the conventional HPC, but also for the public LLM. And the HPC is one representative, the very efficient use on the HPC on the supercomputers. And also, yeah, not only for the HPC, right, or language models are having the hardware software design on the HPC clusters. And even further, we see the cross-site integration, right? Because in addition to the accelerated use of one single supercomputer, we more have a multi-site. They are just in close collaboration to serve the user needs, and also we connect the HPC clusters to the facilities for AI plans, right? So here is some efforts, and including the network A3 program, right? The Dr. Moon just mentioned in the morning, right? It's a collaboration between China, Japan, and Korea. So that's the backgrounds, and we can see that the environments, I mean, the HPC environments are becoming very messy, and nor users have a very evolving needs, right? They want to avoid the bare metal use, and they want to have the cloud-like experiences. So this is the demands, and targeting the demands, yeah, with the NCCGZ, yeah, the National Supercomputing Center and Control, yeah, also have done some efforts, right, including the PC system. We just upgraded the system from Canada 2 to Canada 3, and also we provide virtual PC and internet resources, and also yeah, some third support, the representing once the the starlight will be introduced here. Yeah, it's a Discord starlight. It is basically a DC class AI integrated platform for the users. So it means you can run the PC and AI applications very conveniently. So basically, it's a containers as a service. And the top of the starlight, the infra, yeah, we want to do one step further just for exploration. I mean, just to explore some practical uses. So here our goal is to build an independent practical platform initially just for the task staging, for the practical training. So we just integrated a full cycle development. So you can develop in the platform and then you can run just one stop dev run workflow. And from this year, actually, back in March, I mentioned that the HTC AI, but just it was a percentage. So here I talked it as a percentage of the industry, right? So from March, we just deeply embedded AI or the learning model into the platform. And also we tailored for the sales application and STEM research. And our main effort to simplify the user experience. And here I talk about the overall design. Yeah, this is the overview of the workbench. It is the augmented workbench. Basically, the cloud-native plus the integrated app environment. And we just fused the and the APC. Yeah, here's the overall architecture. You can see the dash CS includes this AG, just the automatic judgment, just for the teaching for the private training. And the bottom language model and the right, just the right search, yeah, to improve the quality. And the first part is the OL just provide the online support. Yeah, basically you have some core capabilities, yeah, unified scheduling and real-time monitoring, yeah, just provide some functionalities. And also, yeah, just it was developed based on the top of the starlight, yeah, the software stack I just mentioned. And we separated the control flow and the flow, and more importantly, for the user support, we can support many kind of users, yeah, just including the administrators and also the students, yeah, the end users. And the workspace yeah, basically just the container based and integrated the cloud and you just log into the web page and then you can develop the code there with the and just beyond the other containers, because it's a left side of automation and automatic environment setup. So it means you do not need to set up anything, you just log in and use. And further, you decouple the data and the runtime, the right figure, yeah. But for more, we are also developing for some intelligent application service platform. Yeah, and also the simplified user experience. And this part is the ACC-LM, just a smart engine to embed the LM for the infra, on PC, just locally install the PC, and we deploy the PC where the VLM, and also we provide the unified HCI and tool management. And this part is just the simulation of the whole system, because it will empower the intelligence of all kinds of uses. And here are some intelligent uses, including the smart coding assistant and RAG enhanced question and answer for personalized learning, and also the automatic research agent. And here's the one specific example, the coding with RAG. Yeah, here's for the particular training. To mean the student what's the content of the experiment or the S2 answer it in English. Yeah, so here it will answer very specifically to the experiment we assigned to the student, because it is on the RAG. And further the inversion scenarios, yeah, because we say deployed on the PC, we can provide for training, just for very general uses. Any our user, just can learn that because the use cases can be assignment assistance, big technical or many things else. And the folder stand for coding, right? We just integrated VS Code, and it can provide the entire coding tools, the debug or the our coding completion. And further, we want to go further for creativity. So it means users can do some more creative things, right? Like the area generation and the research planning, like the automatic written papers and the key methods from the paper and the general research questions and technical plans. And also, it can be for coding, parameter design and data analysis. And also for the results output and the reproducibility. That's for the open science or the open science researches. And putting together, we have the cross stage empowering, just to build the digital research ecosystem, bringing the tool and data barriers so users can just import the data into the info and then just to everything that's here in one stop uses. So some are cases, just roughly introduce cases. First, because this was initially designed for education, so more applications also still used for the education. The representative case is the combination training. So it means students will learn how to craft the technical compiler based on the open source industrial compiler. So generally, here we provided practical model and developer friendly experiences. You will bring the quality teaching with the industry needs and also define the modern standardized environment. And also you provided the intelligent and collaboration practice support. So here, if you access the data, you can see the content here, right? Just the left part is just the right introduction of the CDN, and left is the just the real use of the CDN for education. So basically, with ASCDN, or you can quickly stream the new batch to expert the capacity boosted by the LMs. The learning test 3 levels for checking, for coding, and for compiling. And beyond the application, more is also being crafted for research. So basically here we serve as a research info or scientific information. So means we will handle the research challenges and the heterogeneous resource management and also the underlying scaling or the complex stuff. We will have that, and then we will enable the users to some creative explorations. So that's the goal. And this part is still under development. Yes, hopefully next time I can report this part in depth. So just to briefly summarize, the local box, the enhanced supercomputer bench, boost for the smart education and research. And hopefully, later we can empower more integrated innovations. So, okay, thanks. That's pretty much of that.
Thank you for a really good presentation. Our next speaker is well known to all of us in the APAN community, Dr. Werechai. And she'll be presenting on forest and AI.
Wait a minute.
Okay.
And Meg, hold the pen.
Yes.
Yes, I have to find his file.
Yeah, okay.
So maybe I just while finding the first about the update of the what we have done with the forest fire control or fire mitigation and fire control in public. So we have been working with NASA, NOAA for a long time since they launched the Terra model in 1999. We are using the products, the active life product for them, and it's improving. So we try to improve from the time of after the detection, so the time that deliver to the firefighter in the field, so they can control the fire and suppress it as soon as possible. That because that is the point of having the fast detection. I just came out a little bit late because there's another thing that there's another talk that they are using. Yes, thank you. Using the camera to do it so it can be faster. So you have a thermal camera on the ground to do that, and with the AI detection in the cloud, and then you can deliver that to the authority, whoever that's responsible to control the fire. Then it can be better as soon as possible. So this is the update thing, and then those logo is just the people that we're working with for this thing, and then we have the 3 university from France that they have a graduate student that I took interns, like 3 of them each year. So they just come over and then work on the related forest fire, whatever you want, but it has to be related. So last year we had 3 developed system from whatever we request NOAA to send our information to us faster than NASA. Then they develop a webmap server to present that, and the authority can use it. Okay, and then this year, another university, they know about it and they would like to come and then just improve whatever they done it last year. So the student who the name Leah, very difficult to pronounce the French name, is and then Trudeau and me, they're from inside Renaissance University. There's one of them usually is from the computer engineering program of school. So this is the contents, and go quickly. There's a problem with the fire danger rating system in Southeast Asia. The one that they're using currently is calibrated by Canadian Forest Service, but it's for the peak fire. So it's good for Indonesia and Malaysia, but not good for Thailand and upper ASEAN like Laos, Cambodia. So we recalibrated at the request from Bill the Good, who is the boss in Canadian Forest Service 10 years ago. Then we did it, we used it, and we, I think 4 or 5 years ago, found out we got the equipment, put in the field, try to validate it, and not correct. Published 2 papers, but like strange. But okay, you admit it is not correct, so we try to recalibrate it. So we went back to Canadian Forest Service. Natalie Jacko and then Mike Watson is the one who doing this audit. I mean, number 1 now, Canada. So they agreed to help. So we send the data, 30 years of the data, of the weather data for Thailand to them to recalibrate it that way. Because after discussion, Natalie said, your 2 papers wrong, or wrong. Okay, it's fine. So they recalibrated for us for 2 years. And last year they sent us the new threshold, but we couldn't test it because we have internal problem. So we have to solve that with the different department. You know, this is mine, not you, blah 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 blah. So still, so this is just to show this is the old. Okay. It's delayed. It's delayed. Okay. So this is you. Sorry. Why is delayed? Directly from you. Okay, now don't touch it. Okay. Like Jamie said, don't touch it. We went up again this morning. That's why we start late. And the problem all over the same thing again. Like, oh, why are you here? It's like, okay, same thing. But this is under construction because of the ownership thing. But it belongs to the department and the other department, something like that. So they're both under the same ministry. So this next one that we're gonna have gonna go up to the ministry. So no more argument. But we still have to wait for it. And the system can handle upper ASEAN with the new threshold. It's the same as ASEAN, just different threshold and using different input from the forecast, from the hydroinformatics, the weather forecast. So we can do like the advanced warning, early warning system. And the actifier, as I explained before, we got the request that can get faster than NASA. Richard Schroeder is the one who wrote the code, fire code. And NOAA is the owner of the satellite. So we can get maybe half an hour faster than NASA. It's just also the same thing, the latency. There's agreement between NASA and NOAA that the satellite, NOAA, assuming NPP, NOAA 20, NOAA 21 that they use for fire, it belongs to NOAA. So NASA can have data at the same time to distribute it. They have to wait until NOAA distributes it first. Then there's an internal agreement I found out. So we used to use a firm. Then I know that Richard Schroeder. So can you do this? Because we need, in the theory, we need detection information as soon as possible, so people in the field can you fire and then suppress the fire, control the fire. So and then we got it. So now we can have the information at the same time that US Forest Service can have. But you need the complimentation letter, very nice one to the director, something like that. So this is the website that the French intern did it last year for Thailand, and now it's expanding. Okay, you click it, anyone? I didn't touch it. Okay, so we did it for Thailand, and then we expand to Cambodia and Laos, and the one that with the logo, that's we have to ask permission. Oh no, they have to request. All of them have to request. And then this year, Ahogo, then now you do the Ahogo, the Korean side, then they find a lot of country in the region to do the project. Yongjun Lee request that would like to have it for Vietnam because the regional office is in Hanoi. You just want to show something. Like, okay, fine. Yeah, we just put it for you, so you can just use it. So this is just like to just present those email that we got it from NOAA, more user friendly. Okay, and that's just that. And then this is like just an example that the Royal Forest Department using in their daily, in the morning to make the planning, and in the afternoon to see the monitor how the fire movement before they deploy firefighter in the forest. And we have this, we're doing this with the global fire situation. This year, not me, last year was me and Bambang in Indonesia. This year, the Russian professor will do it, and the Chinese. But we do it for Asia, Southeast Asia part. But too many, you need to see the name. So we decided just put, you cannot put everybody in there. So we have meeting, okay, select 2, okay? It's gonna be much less than that because it's the whole, too many people. So, and this is a student, 2 of them sitting at the Hydroinformatics Institute. One is online. He don't want to come, something. And this is the Andrew thing that we are requesting. We have problem with the processing the burn area product, and Andrew already hosts the Sentinel-2, and then we can, if possible, we can use the facility to process it just there and take the product and use it. You start for Thailand first, everything started, and then we can expand to Upper ASEAN, so Myanmar, Laos, Cambodia, and Vietnam. But this is one thing, free. That's the thing, yeah, free for them too, everybody. That's just that, so it's a bit difficult to really push it, but, if we don't do it, nobody do it. Just very strange, feels like a lot of things, they like, second phase. But we'll see, but if Andrew could be kind, push it, then it's gonna be great for us. And we will, the problem is that we will validate. We will validate the algorithm to use the detection. It's not the same, okay, vegetation is different everywhere. So you can detect peat fire, but when you detect the surface fire is different, cloud fire is different. Also the same thing with the burn area. I just recently, a month ago, a European Space Agency came to Thailand. We had a talk, because they come to the Thai Space Agency, but they stopped by to at Royal Forest Department, Department of National Park, and Hydroinformatics Institute. I'm asking for the burn area mapping by microwave, Sentinel-1, but because Indonesia, they have a lot of cloud. So you cannot have the optical system to do it. You have to integrate it with the microwave. But even then, it's still cannot. So anybody they can think about it, because the owner is still like, how difficult. Okay, this is just a development for the new website. That the previous version is static. This one will be interactive map. So much easier for user, and those two intern, they will have to finish before first week of next month. Have to evaluate it and they will go back. But now I don't want them to sit in the the room doing it. They go around Thailand, and they said they're gonna go to Laos, to Vientiane, to Luang Prabang. They go, but at the end of the week, report please. This week not yet. You'll see. Okay, that's just an improvement. And for conclusion, we usually don't, still not enough understanding of the fine sign and small sign. Still, anybody can say anything, but the one who studied for 100 years, okay, just for example of fire behavior, the place, Mozilla Fire Lab, Mark Finlay, the best now in the 5 years, he's still studying, and he started the cooperation with Google. So that's why they're gonna launch FireSat, funded by Google, a small satellite, at least 50 of them. But that's for Google. German, Aurora Tech will also doing it. Australia will also doing it. Canada government announced that they will do it, because and it's probably going to be constellation. The aim is like 10 to 15 minutes detection by satellite globally, so people can just help each other, because now you see the new, right? Make a fire and then kick a fire. Now I heard the word, the new one, kick a fire. If you could control it when it's small, then it's not becoming big. When some side are able to control, for example, in Korea this year, the people from Korean Forest Service, they'll be talking to the fire to control it, and they are from the aviation people, cannot. It's too big, and you just send the clip, take a photo, send in. If the wind too strong, it's dry. Even they have, I don't know now, maybe 60 helicopters ready to go. Cannot. So if we could detect as soon as possible, and then send someone to, control it when it's small. So still, that's the problem. Smoke also have the smoke air quality thing, big thing now, but still need to really study. They have a plane going around, and then collect and change it. Anyway, it's the problem. We use the collaboration, and the fund is not that much actually. And then we have too many. The theory, garbage in, garbage out. It doesn't matter how good you are. It's too many now. There's a problem that we have another working group open and sharing. We try to emphasize the sharing of the data, but the problem is good data. It's too many. But people, they don't know. They just ask Google and then follow that, which is not good in the long run. You couldn't fix it now, but you live like that, like you look so many bad math, because easy to make math now, used to be very difficult, I studied probably to make math, difficult. But now, anybody can do it, use the software, but they don't understand how to make the math. So when they make the math, mark them out, in our turn, but that's the way to have it, okay, thank you very much.
Yes, I wanted to add in one comment. I just invited him to present in here. And in case of NIP, and they have the wildfire project, how to detect wildfire in California and the mountain area. They're using a sensor and drone and the satellite data, even though the AI analysis model. Because we discovered this just one small red dot of fire, and the humans cannot distinguish this is a fire or a small light. But attention to the deploy the AI analysis, and they distinguish and decide to this is fire, and immediately to the all of the signals to the fire, the police and the governors, and the reaction to the prevent this wildfire.
In the new good example, Los Angeles fire.
Yeah.
When they detect it very small, but I don't know why they didn't attempt it, and then the wind chill. When the wind chill is like, then you cannot control it. So,
Yes, this
so
area is one of the.
you are too late.
One of the target areas for such like APRP and NRP and KRP and such like platforms to deploy in that areas. Thank you for your.
Thank you for having.
And Angela, maybe I think it's the last one is word cancer then.
Oh, okay.
Yes, yes.
Sorry, boss.
As both John and Charlie mentioned, fire events are becoming more and more prevalent in all of our countries. And I think it would be really good if we were able to devote some of the APIP resources, our skills and technology, to kind of support the lack of funding that we're seeing in this area. I'm going to work with our federal government to have them provide some additional tools and funding capability, and hopefully we'll be able to answer the email that Charles wrote on the screen.
Keep quiet.
Yeah.
If you want.
Support this account. I think that brings us to the end of our program. Month is served. Please ask questions for anyone who's presented, or just let us know what cool stuff you're doing. But thank you again for joining the APRP working group, and thank you for coming to APAN60. Hopefully we'll see you all in APAN61. Thank you very much.
Thank you.
Thank you. Thank you. We shouldn't be confident.
Biggest thinking.
Let's have lunch.
Hi.
You maybe access from here.
Here.
Yeah. So yesterday actually I have some problem with this room
Yeah.
in general. So it will be solved.
It's all worked out. It's all good now.
So.
Okay.